So let's go ahead and look at 3/6. We'll finish 3/6.
At least you feel cool when you get on that. Maybe. Or you feel stupid because you get around. But, well. Okay, so let's look at example 3. So as I look at example 3, we want to graph this. So I gave you those multiple steps yesterday. So as I look at 3, let's go ahead and just go through my steps. So step number 1 is the domain and range. We don't really worry about the range necessarily. Usually it's not going to be super helpful. Domain is what's going to be most helpful. So as I look at this domain, I notice I have a rational function. I kind of have both things going for me. I have a rational function and I have a square root. So as I think about it, let's think about it. Let's start with a rational function. Is there any way I can get a 0 in the denominator? So as I look at this, is there any way I can get a 0? So how I would get a 0 in the denominator is I would get something -2 plus 2. So is there any way I can square something and get a -2? No. So there's no way I can get a 0 in the denominator. Then let's look at my square root. I cannot take the square root of a negative. Is there any way that I can get the square root of a negative down here? Is there any number that I square plus 2 that will give me a negative? No, because what's going to happen, even if I plug in a negative x value, what's going to happen? It's going to turn positive. So there's no way I can take the square root of a negative. So my domain is going to be -infinity to infinity. So this one, even though you had a rational function and a square root, there's no way to get a 0 in the denominator or the square root of a negative. So my domain is -infinity to infinity. So that's step 1. Let's go ahead and look at step 2, which was, I forgot what I wrote down yesterday. Step intercepts? Yeah. Is that right? So x-intercept, we're going to set it equal to 0. So plug in 0 for y, which means I really only necessarily worried about the top part. If I set a rational function equal to 0, the bottom is gone because you can multiply both sides by the denominator. So I just get 0 equals x. So my x-intercept is at 0. Not too bad. If I look at my y-intercept, plug 0 where x is. So 0 over square root of 2. So it's just 0. So if my x and y-intercept are both at 0, then it's just going to have to go through the order pair 0, 0. So it's going to be my x and y-intercept, 0, 0. So it's going to go through the point 0, 0. So I like graphing it as I go through it. The next thing I looked for was asymptotes. Correct, I think? I'm trying to do it from memorization. So vertical asymptotes, not too bad to find. We're looking at what values give me a 0 or what x values cannot exist, which you kind of think about when you do domain. So do I have any x values where this graph can't exist? No, because my domain is -infinity to infinity, so there is none. There you go. My next one, horizontal asymptotes. If I look at my horizontal asymptotes, use this shortcut if you can. So as I look at this, we always want to try to use the shortcut if we can. The shortcut we use by looking at the degrees. So the degree of the top is what? 1. What's the degree of the bottom? That square root messes you up. I don't have a polynomial because of the square root, and you can't just take the square root of x squared because you can't take the square root of them separately. So there's no really way to use the shortcut on here. The reason is because I don't have a polynomial in the denominator, so I can't easily tell what the degree is. Does Sorry, I'm flipping it all off. You can't easily tell what the degree is, so we have to do the longer way, the limit way, to find the horizontal asymptote. So if I want to find the horizontal asymptote using the limit way, we're going to take the limit as x goes to infinity. Now you could do negative infinity. It's either one of them. I usually just do infinity because it's a little easier. So we have to use the limit way because I don't have a polynomial over a polynomial. If you do, you could just look at your degrees and then use those three shortcuts. Since I have the square root in the denominator, I cannot do it that way. So I have to do it the limit way. So I'm going to take the limit of this. And what's kind of my strategy if I'm taking the limit to infinity or negative infinity of a rational function? We did a couple days ago. Divide everything by the highest exponent in the denominator. So we're going to take everything, divide by the highest exponent in the denominator. So if I start in my denominator, that means I'm going to take everything and divide by x squared. Now in my numerator, we can do this because I'm taking both things dividing by x squared. So since both things are being divided by x squared, what am I really going to be taking the top dividing by? X. Like we did in the notes a couple days ago. Since I have the square root of x squared is an x. So the top is technically going to be divided by x. So if I go through and simplify this, we have 1 over the square root of what? 1 plus, and now if I take the actual limit, you can do this step together. The limit of a constant over x to any power, 0. So 1 over square root of 1 is 1. Now, if I think about it, we also want to look at the limit as I go to negative infinity. So if I think about it as I go to negative infinity, now I told you earlier we had to do 1, just 1, that is fine, but you're going to notice as you go through that it might go, negative infinity might go to another limit. And you could kind of see that as you start going through. So it's kind of a good idea to do both of them. Basically, the only thing that's going to be different, we didn't want to like it in the notes, is you're going to have to throw a negative on there. So basically, it's the same thing. That square root will just be a negative because I'm going to the left. So I'm only going to be worried about the negative square root. So that's why it's just going to be a negative 1. So you can kind of take that shortcut, but anytime I'm dealing with the square root, and I'm going to infinity or negative infinity, it's a positive 1 and that negative 1. So my horizontal asymptotes are at 1 and negative 1. And I'm going to go ahead, I'm going to make 1, 4 up, just so we're not all scrunched together on the graph. I'm going to go by 4s. So I'm going to go up 4 to get 1. I'm going to go negative 1. Down 4 to get negative 1. Just so we're not all scrunched. So be careful, if I have to do the limit way, if I have a square root, when I go to negative infinity, it's going to be a negative, whatever you get. Okay, any questions so far? Okay, fourth thing is I check for symmetry. So plug in a negative x and kind of analyze that. So negative x over square root of negative x squared plus 2. So if I look at this and simplify this, I have a negative x over square root of x squared plus 2. If I plug in a negative x, do I get back the original? No. If I take out a negative 1, if I factor out a negative 1, do I get back the original? So if I put a negative out front, do I get back the original? Yeah, I do. It's a little hard to see because it's the square root, but yeah, I get back the original. So if I take out a negative and put it out front, I get back the original. So since if I take out a negative and get back the original, this is symmetric with the origin. So that is hard. Symmetry with the origin is a little harder. All that means is you can rotate it around the origin and it's going to look the same. So if I rotate it 180 or halfway, it's going to look the same on the left and right. So it's a harder one to see, but when we draw the graph, you'll be able to see why it's symmetric at the origin. Okay, let's look at number 5. If I look at number 5, that's when we start finding my max and mins, critical points, increasing, decreasing, which is all included in the first derivative set equal to 0. So let's take the first derivative. If I try to take the first derivative, we're going to have to do quotient rule. You could manipulate it and do the product rule. I'm just going to keep it and do the quotient rule. So x over x squared plus 2 to the 1/2. I'm going to rewrite the square root to the 1/2 power. And then let's go ahead and take the quotient rule and set it and take it equal to 0. So low x squared plus 2 to the 1/2. D high, which is 1, minus high, which is x, d low, which is going to be the chain rule, 1/2 x squared plus 2 minus a half as my exponent, because I subtract 1, times the derivative of the inside, which is what? 2x. All over square what's below, which is going to be what? X squared plus 2 to the 1/2 squared. What's the square of what's below? What's the square root of x squared plus 2 squared? X squared plus 2. So that cancels out nicely. So when I square the denominator, that cancels out. The square root cancels with the square, so that's just x squared plus 2. Now, as I simplify this, let's simplify this. You can kind of do this if you can see it. You don't have to simplify it. Well, let's just simplify before I factor stuff out. X squared plus 2 to the 1/2 minus 2.5 will cancel, so I'm going to have x squared plus 2 to the negative 1/2 over x squared plus 2. What can I factor out of the top? X squared plus 2 to the negative 1/2, which will leave me what left? Yep. Yeah, x squared plus 2 to the first, because negative 1/2 plus what will give me a positive 1/2? 1. So that's just x squared plus 2. And then my second term, I'm just going to have a what? Negative x squared. All over x squared plus 2. Okay, now I'm just simplify it as much as I can before I set it equal to 0. If I simplify it a little further, we're going to have, what can I do with the x squared plus 2 to the negative 1/2? Kind of cancel out, not really cancel out. Where am I going to have to move that x squared plus 2 to the negative 1/2? The bottom. And if I already have an x squared plus 2 to the first, I'm going to have an x squared plus 2 to the what in the bottom? 3/2. When you move them down, you add the exponents. So 1/2 plus 1 is 3/2. And the top is just going to be 2. So that is my first derivative. Now if my simplified first derivative. So you want to simplify it all the way, keep the denominator, so when you plug in to check increasing, decreasing, you know you have an easy one to plug it into. Now if I set it equal to 0 to look for my critical points, I'm only have to worry about the top being equal to 0. So if I set the top equal to 0, what do I find out? Yeah, I don't have any critical points. So I have no critical points, because this does not work. 0 cannot equal 2. So I have no critical points, which only tells me that I'm not going to have a what? If I don't have any critical points, I'm not going to have any... Yeah, I'm not going to have any max or mins. I'm not going to have any extrema. So I won't have any max or min. So as I kind of draw my graph, I shouldn't have a definite max or min. And it does tell me, critical points alone doesn't tell me that it's going to be increasing or decreasing the whole time. But if I look at my domain, why do I know that it's going to either be increasing or decreasing the entire time? Do I have any breaks in my domain? No. So there's only one interval to check, negative infinity to infinity. So since there's no critical point and since there's no breaks in my domain, there's only one interval to check for increasing or decreasing, so it's going to be doing the same thing the whole time. So as I look at this, plug any number in there into the first derivative, which is this 2 over blah 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 to the 3 halves. Plug in a 0. If I plug in a 0, do I get a positive or negative? Positive. So this is going to be increasing on the entire interval, because there's no critical points and there's no asymptotes, there's no breaks. Any questions on that? Okay, now if I look at the second derivative, which I'm going to kind of squish in here, that's number 6. So as I look at my second derivative, use the most simplified first derivative, which is this 2 over x squared plus 2 to the 3 halves 1. Now if I look at that, I could do the quotient rule, which is a little longer, but you'll get the right answer. I could also just do what? Bring the what? Yeah, bring the bottom up. So I could just rewrite my first derivative as 2x squared plus 2 to the negative 3 halves. So if I use that shortcut, that saves me a little bit of work by just having to ignore the quotient rule. Basically, I'm just going to use the what now? Not product, because 2 is the constant. Chain rule. So we don't have to do the product because 2 is a constant. If it was 2x, I would have, because it would have been a function times a function. So now I just have to do the chain rule. 3 halves out front, so 3 halves times 2, negative 3. Inside stays the same, x squared plus 2. Reduce it by 1, so negative 3 halves minus 1. Negative 5 halves times the derivative of the inside, which is 2x. So if I simplify a little bit, negative 6x all over x squared plus 2 to the positive 5 halves when I move that to the bottom. Okay, next one, let's go ahead and set it equal to, I need to find the second derivative equal to 0 to find my inflection point. So if I set it equal to 0, this isn't really a hard, I just worried about the top. So 0 equals negative 6x. So I have an inflection point at x equals 0. Divide by negative 6. So I have an inflection point at x equals 0. Which tells me that I'm probably going to switch concavity at 0. Which makes sense that I have an inflection point at 0 because that's where I have the intercepts as well. So as I check concavity, what is going to have to be the intervals that I check concavity over? Negative infinity to 0 and 0 to infinity. So unlike the critical points, I actually have an inflection point, so I have to include that in the interval. So plug it into the simplified, make sure you include the denominator, simplified second derivative. So if I plug in a -1, positive on top, I'm going to have a what on the bottom? Positive, so it's going to be concave up from -infinity to 0. 0 to infinity. If I plug in a 1, negative over positive, so that is concave down. So it is going to switch concavity once it hits 0, 0. So now if I graph this, start from your left, it's increasing the entire time. I'm concave up from -infinity to 0. So I have to be approaching that asymptote because as I go to the left, I'm approaching -1. Has to be concave up, so it's going to be like a happy face, like that. And then from 0 to infinity, I'm still increasing, but I'm concave down. And I have to be approaching 1. So something like that. Okay. Questions so far? Okay. Let's go ahead and look at example 4. Just by looking at example 4, why do you kind of breathe a sigh, or sigh, I don't know what to say. Breathe, no. Sigh of relief, but do I use breathe in front of it? Because that's kind of redundant. Yeah, okay. Anyway, I don't know. I can't talk today. Ignore that. So, as I look at, sorry that I'm awkward. As I look at example 4, it's a polynomial. So that makes my life a little easier. I don't have to necessarily be worried about rational functions. The domain is going to be a little easier to get. I'm not going to have asymptotes. So my life plus taking the derivative and second derivative should be a little easier. So let's go ahead and go through those steps. So step 1, my domain. It is a polynomial, so my domain is what? -infinity to infinity. Almost always polynomials will have -infinity to infinity as your domain. The range will also be -infinity to infinity, which we don't really care a ton about the range, but technically it would be. The second thing is my intercepts. So x-intercepts, 0 equals 2x to the 5/3 minus 5x to the 4/3. So I set y equal to 0. So I try to solve this. The exponents are weird, so I'm not really sure how to solve this. Any thoughts on what I can do? An x to the what? Lowest exponent? Yep. I notice I can factor out an x to the 4/3, so don't get kind of caught up in the, I see these weird exponents. Still think about factoring out the lowest exponent like I did earlier. So this is going to be 2 to the 4/3 plus what? X to the 4/3 plus what? Because I am multiplying gives me 5/3. 1/3, yeah? And then it'll just be a minus 5. So now I have it factored, so I can take each part and set it equal to 0. 0 equals x to the 4/3. 0 equals 2x to the 1/3 minus 5. And let's think about it. What to the 4/3 power will give me 0? 0. So x equals 0 from the first one. And then let's go ahead and solve this. Add 5, divide by 2. So 5 halves equals x to the 1/3. It's a weird one. What do I do to solve for x? Yep, not cubed root, because it's already technically cubed root. I'm going to cube both sides. Because if I cube it, that's going to cross out. That's going to cancel out the 1/3. Does that make sense? So yeah, I think you're on the right track. So if I cube both sides, I'm going to have 125 over 8. And then I would just plug that in your calculator to kind of estimate where it would be, which is like 15.63. So if you get a funky fraction like this, just plug it in so you can kind of estimate on the graph where it would be. So I'm going to cross the x-axis at 0 and 15.63. So if you want to, I'm going to go by 2. So if I actually graph these x-intercepts, I have an x-intercept at 0, and I'm going to go by 2. So 2, 4, 6, 8, 10, 12, 14, 16. So if there is 16, 15.3 will be somewhere right there. Doesn't have to be perfect, but I'm just going by 2 so I can get that 15.63 in there. Any questions? Okay, now let's look at my y-intercept. If I plug in my y-intercept, you can kind of guess. If I have an x-intercept at 0, I should have a y-intercept at 0 as well. So let's just double check. So y-intercept, if I plug in 0, I'm just going to get back a what? 0. So my y-intercept is 0, which is already graphed. If you have an x-intercept at 0, you will always have to have a y-intercept at 0 as well. Okay, questions on that? Okay, third thing is asymptotes. So vertical asymptotes. Any x values that won't work? No? So none. And horizontal asymptotes. Do I ever have horizontal asymptotes on a polynomial? No. So vertical asymptotes and horizontal asymptotes are usually only when we're worried about rational functions. That's usually where they come from. Step 4 is symmetry. So if I plug in a negative x, I have 2 negative x to the 5/3 minus 5 negative x to the 4/3. Now this is weird with the exponents. Remember, rational exponents, the denominator is your root. So I'm saying I have the third root of a negative to the 5th. So if I take the third root of the negative, that will keep it a negative. If I raise it to the 5th, that will still keep it a negative. So this will turn into a negative 2x to the 5/3. And let's think about this. Third root of a negative will keep it a negative. Negative to an even power will turn it a positive. So that's going to stay a positive. So I'll still have that negative 5 out front though. So the rational exponents, think about the bottom, because the denominator is root. So it's the third root, and then raise it to the numerator. So, is it the same thing? Do I get back the original? No, because that negative 2x part. So it's not symmetric with the y-axis. If I take out a negative 1, is it the same thing? No, so there's no symmetry. So sometimes there's symmetry, sometimes they're not. Not one of the most important things, but it can help you kind of tell if you're on the right track. Okay, any questions so far? Okay, let's look at 5. We're looking for critical points, extrema, increasing, decreasing. So first derivative, set equal to 0. So the nice thing about taking the first derivative is it's a polynomial, so we're not going to have to use any of those stupid rules. So first thing, first derivative of 2x to the 5/3. 10/3, multiply 2 times 5/3, and then 5/3 minus 1. Yep, 2/3. Minus 20/3 x to the 1/3. Okay, let's go ahead and simplify this as I think about setting it equal to 0, kind of like we did similar. What do I want to do first? Factor out a Yeah, look at your coefficients. What can I factor out of the coefficients? 10/3. That'll actually factor out too. 10/3 x to the 1/3. So factor it out like we did earlier, because then you can take each part and set it equal to 0. So now if I take each part and set it equal to 0, I'm going to have, let's see, x to the 1/3, because you add your exponents, so 1/3 plus what gives me 2/3, 1/3, minus, what, 2. Okay, set each part equal to 0. If I take my first part equal to 0, I'm just going to get a what? X equals 0. If I take the second part, add 2, so 2 equals x to the 1/3. Do what to both sides? Cubed each both sides, so 8 equals x. So I have critical points at 0 and 8. Now, like I said, I want to actually know those points because that's going to help me with the graph. So let's plug those x values into the original because I want to know what are the y values. They're critical points, so I'm thinking they're going to be high points or low points, relative max or mins. Let's plug them into the original to see what the y values are. If I plug in 0 to the original, we already did it. I'm going to get what back? 0. If I plug in 8 to the original, that's going to be a little tricky. Let's write it out. 2, 8 to the 5/3 minus 5, 8 to the 4/3. So that was kind of hard. I'm actually plugging it in because it's kind of hard with the rational exponents. Let's see what I have. Third root of 8. Denominator becomes your root. So what's the third root of 8? 2 to the 5th. 32 times 2, 64. Just be careful with those irrational exponents. Third root of 8. 2 to the 4th. 16 times negative 5. Negative 80. So that would be negative 14. So actually get ordered pairs because that will help you when you graph it. To have specific ordered pairs. 16? Sorry. Yep, can't add. 16. 16. Okay. Now let's go ahead and find my intervals of increasing, decreasing. So what's my intervals going to look like? Yep. And 8 to infinity. Take into account the domain, which is negative infinity to infinity, and then plug in your critical points, 0 and 8. So now as I check these, use the, it doesn't really matter. This top one might actually be easier to plug it in the factored form. If I plug in a negative 1, well, actually, with the factored form, be easier. Yeah, factored form might be easier. If I plug in a negative 1, negative 1 to the 3rd, still keep it a negative. So I'm going to have a negative times negative to the 3rd. Negative, so negative times the negative is positive, so this is going to be increasing. If I plug in a positive 1, positive times if I plug in 1, negative, so it's going to be decreasing. And let's plug in an easy one to check. What's it that I could take the third root of? 8, what's the next perfect cube? 27? I don't know, whatever, it doesn't really matter. Cubed root 27 to the 3rd is 3, so this will give me 10 out here. 10 times positive number, positive, so increase. So you can choose whatever you want. I don't really care about a specific number, just positive or negative. So that tells me increasing, decreasing. Any questions so far? Okay, step 6, second derivative, inflection points, concavity. So So as I take the second derivative, I would use the one that's still in the polynomial form. Don't use the factor form because you have to do a product rule. So if I do the second derivative, I will get a 2/3 times 10/3. 29ths, x to the negative a third, 2/3 minus 1, negative a third, minus 20/9, x to the 1/3 minus 1, negative 2/3. Good. Set it equal to 0. Let's factor this. What can I factor out of both of them? Negative 2/3, lowest exponent. So 20/9, x to the negative 2/3, lowest exponent. Now let's see what I have left. I took out the 20/9. Negative 2/3 plus what will give me a negative 1/3? To the negative 2/3 plus what will give me a negative 1/3? 1/3 minus, well, this is just going to be a 1 because I took out the 20/9 and I took out the negative 2/3. So if I set it equal to 0, my chunk out front will give me x equals 0. This chunk, if I add 1, so 1 equals x to the 1/3, cube both sides, so x equals 1. So my inflection points are at 0 and 1. Let's get actual ordered pairs. At 0, I know it's going to be 0. We already did that twice already. If I plug in 1 to the original, I'm going to get back negative 3. 2 minus 5, negative 3. So it's helpful to have actual ordered pairs as I go through and try to graph it. And let's go and check concavity. So my intervals I need to check for concavity are going to be negative infinity to 0. And what is it? 0 to 1 and 1 to infinity. Okay, so let's check. If I plug in a negative 1 into the second derivative, let's see what I have here. It's going to be a little hard to think about. Negative 1. So negative 1 to a negative 2/3. If I move it to the bottom, so negative 1 to a positive 2/3 will give me back a third root of a negative squared, positive. So this will be a positive times a negative. So it will be concave up. That will be a positive. Zero to 1, let's just plug in a half or something to think about. I don't need a specific number. So if I plug in a number between 0 and 1, it's positive. So I will have a positive out front, and I will have a what inside here if it's between 0 and 1? Negative, so concave down. And then from 1 to infinity, if I plug in a 2, I will get a 1 over, I'm going to get a positive, and I'm going to get a positive, so concave up. So that one's kind of hard to think about. Okay, any questions so far? Okay, let's graph this real quick. Let's go ahead and graph the inflection points and critical points. I haven't done that yet. So I have a critical point at 0, 0. I also have one at 8, negative 16. So 1, 2, 3, 4, 1, 2, 3, 4, 8. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. I'm going by 2's. So there's my inflection point. 8, negative 16. I already have 0, 0 on there. And then let's go ahead and plug my inflection point. So 0, 0, and 1, negative 3, which is going to be right there because I'm going by 2. So it's going to be over halfway, down halfway between 1 and 2. So now let's go ahead and graph this. So as I graph this, I don't have any asymptote, so I don't have to be approaching something. But as I look at this, from negative infinity to 0, I am increasing and concave up. So something like that. I'm going to have the smiley face curve, and I'm increasing. Doesn't have to be perfect because it's not approaching an asymptote. From from 0 to 1, I am decreasing, because from 0 to 8 I'm decreasing, so I'm going to be decreasing, concave down, so frowny face, so something like that. I'm still decreasing from 1 to 8, but I am, from 1 to infinity, I'm concave up, so I'm going to switch happy face. From 8 to 8 to infinity, I am increasing, and I'm still concave up. And it has to cross at 15 point something, something, something. So something like that. So make sure you have the concavity here. Concave. This is concave down, so it should have that kind of frowny face curve there. So just be careful with that. Any questions on that? Okay, one more. We're going to do one more polynomial, and then we'll be done for this section. Woohoo. Okay, example 5. We're not going to do example 6, so if you need to go down in that section, that's fine. So example 5, I have a polynomial. I know these take a while, but like I said, I did the harder ones with you yesterday. Example 5. As I look at example 5, it is a polynomial. It's not rational. I do not see square root. So as I start thinking about it, it should be not too terrible to accomplish. First thing, what would you do first here? Distribute through the negative a third. So negative 1/3 x to the third plus x minus 2/3. Let's just do that first. Makes your life a little easier. Now, as I look at something, sometimes I'm going to use the factored form, sometimes I'm not going to. It just kind of depends. But we can have both forms, and we can kind of switch between them depending on what I want to know. So as I look at my first thing I look at is my symmetry, or my domain. Domain is going to be what? It's polynomial. Negative infinity to infinity. My range will also be negative infinity to infinity because it is a polynomial. So polynomials almost always have both negative infinity to infinity. Second thing I found were my intercepts. So x-intercept, if I plug 0 in for y, now is going to be the case where using the factored form is a little easier to use. So if I set it equal to 0, I'm going to be factoring out a negative a third anyway, so let's just use the factored form. So 0 equal to a negative a third doesn't exist, so I just have 0 equals to the inside part. As I try to solve this, I want to look for my x-intercepts. What issue do I run into? Yeah, it's not x squared. So because it's not quadratic, I can't do quadratic formula. I can't do factoring. Could do factoring, but I already factored out what I could. Can't do completely the square. Can't do the square root principle. How do I find the roots of something if I can't do any of those? Did it in the homework a month or so ago. You might know it and not want to say it, but How do I find the roots of a polynomial if I can't do factoring or quadratic formula or any of that stuff? Any takers? Any takers? Okay, it's the rational root theorem. So we have to do all my possibilities, P over Q. So like I said, I picked examples that had multiple different ways to do it in there. So if I want to do P over Q, what are all my factors of 2? Plus or minus 1, plus or minus 2. You did this in pre-calc and algebra 2, I think. You might have erased it from your memory because it was annoying, but you've done it. So if I cannot find the root by doing, if it's not quadratic, and I can't do any of the quadratic stuff, you have to use the rational root theorem. So all the factors of your last term, plus or minus 1, plus or minus 2, over all the factors of my first term, which is just plus or minus 1. So all my possible roots are plus or minus 1, plus or minus 2 if I divide them by 1. Remember this? Okay. Now how do I start checking without graphing it? Because in Algebra 2, at least in my class, I had you kind of graph it and estimate which ones to pick. Well, that kind of defeats the purpose. Because if we're graphing it anyway, graphing it to see which ones to pick is going to defeat the purpose. So how do I, once I have my possible roots picked out, how do I figure out which ones are actual roots? I'll give you a kiss candy if you remember. I remember? Synthetic division. So if I do synthetic division, we're going to start checking these and see which ones give me 0. It doesn't matter which ones you start with. Let's just start with, I don't know. I'm going to be nice and start with 2. Just because I know. But you would just start plugging in and do it. There's not going to be a ton where you have to do this. But like I said, I want to give you a wide variety on your notes. So if you get one that looks like this on the homework, you at least have seen it. So let's check 2. We're going to do synthetic division. So my coefficients go up top. 1, 0, negative 3, and 2. It's ironic that we're like, oh, it says polynomial, and then they make you do this. But it's okay. So synthetic division, make sure you put your coefficients. Make sure you put a 0 because there's no x squared. Let's see if I get a 0. Bring down a 1. 1 times 2 is 2. Add down 2. Multiply. 2 times 2 is 4. Add down is 1. Multiply 2. Is 2 a root? No, because you do not get a 0 here, so 2 is not a root. Now let's check negative 2. I guess I could have checked plus or minus 1 too. Either one is fine, but I just picked some to start checking. Let's check negative 2. 0 or 1, 0, negative 3, and 2. If I bring down a 1, multiply 1 times negative 2 is negative negative 2, add down negative 2, negative 2 times negative 2 is 4, add down is 1, multiply is negative 2, I get a 0. So negative 2 is a root. So to find my other root, you could keep doing synthetic, or let's rewrite it. So if I have a root of negative 2, when I rewrite it, I'm really going to have an x plus 2, because you always switch the sign. Because if I would set x plus 2 equal to 0, that would give me x equals negative 2. So as I rewrite this, I'm going to have an x plus 2 out in parentheses. What's going to be left in here? How do I figure out for my coefficients at the bottom what's left? Remember? You go down 1 degree. So if my original was x cubed, it's going to be x squared minus 2x plus 1. So we had to do the rational root theorem to find a possible root. Then we rewrote it. Sometimes when I rewrite it, it will be factorable. So how does x squared minus 2x plus 1 factor? Two numbers that multiply to give me 1 and add to give me negative 2. Negative 1, negative 1. So sometimes when you do synthetic once and rewrite it, then you will be able to get to a point where you could factor it more. So if I would have done the synthetic division with 1, it would have worked out 2. You just find them. So my roots are at -2. My x-intercept or roots, which are the same thing, are at -2 and 1. So that was annoying, but I wanted to do one with you where it had rational root theorem in it. Questions so far? Okay, the y-intercept, which is a lot easier, I promise. Y-intercept, if I plug in 0 for x, it's a little easier if you don't use the factored form. Use the one where I multiply through. If I plug in 0 for x, I'm going to get a what? -2/3. So my y-intercept is -2/3, so right there, something like that. Doesn't have to be perfect. I'm going to put -2/3 on the y-axis. Let's see. Step 3, asymptotes. Any asymptotes? No. Polynomials almost always never have asymptotes. Actually, I think they never will. I hate saying never because there might be a time or not, but usually they don't. So no vertical asymptotes or horizontal asymptotes. Symmetry. If I plug in a -1/3, we can use the form where I multiplied through. -1/3, -x to the third, minus x minus 2/3. A negative to an odd power keeps it a negative, so that we have +1/3, x to the third, minus x minus 2/3. Do I go back to the original? Nope, so not symmetric with y-axis. If I take out a negative, do I get back the original? Nope, so I don't have any symmetry, which not a big deal. It just, you shouldn't see any symmetry as you graph it. Let's go ahead and take the first derivative, which isn't going to be terrible, and we're going to use the form where I multiplied it through, because that'll be easier. So if I take the first derivative, I'm going to get back a what? -x squared plus 1. So that's easy to take the first derivative of that. Set it equal to 0. -1 divided by negative, so you get 1 equals x squared. So x is plus or minus 1. Let's check my intervals. So the intervals for increasing or decreasing I need to check will be, Yep. My domain is -infinity to infinity, so I only need to put in my critical points there. I forgot to do something real quick. Check your actual ordered pairs for your critical points. Something I forget to do, but it'll help with your graph. If I plug a 1 into the original, I will get a -1/3 plus 1, which is 2/3 minus 2/3 is 0. So 1, 0. I could also guess because that's a y. 1 is an x-intercept, so I know my y value had to be 0. And if I plug in a -1, I will get back -4/3. I'm not going to go through the work with you for time's sake, but you plug in a -1 into the original, that's what you'll get. So make sure you get actual ordered pairs for your critical points. Let's check. If I plug a -2 in here to the first derivative, I'm going to get back a positive or negative? -2. -2 squared is 4. -4 plus 1. Negative, so it's decreasing. If I plug in a 0, I get back a positive. If I plug in a 2, I get back a negative. So decreasing, increasing, decreasing. Questions so far? Step 6, second derivative, which isn't going to be bad. Second derivative is going to be what? Negative 2x. Set it equal to 0. X is going to be 0. So that was easy. Check my intervals for concavity, which the two intervals I'm going to have to check will be, yep. And let's get an actual ordered pair. 0, if x is 0, all we're looking at is the y-intercept, which I already know is a negative 2/3. So if I plug in a negative into the second derivative, I get back a positive. And if I plug in a positive 1, I get back a negative. So concave down. So let's see what I have here. As I look at this, I have an inflection point at 1, 0, and negative 1, negative 4/3, which is going to be like right here, something like that. It's my inflection point. And then I have a concave. So let's look at this. You can also look at end behavior. So if this is x to the third and there's a negative in front, from pre-calc, it's to the third, so it's going to be opposite directions, and it's a negative in front, so it's going to be like this sort of end behavior. So you can kind of use end behavior if you have a polynomial with an even power, it's both up or both down. Odd power, they're in opposite directions. That negative flips it. So I know it's going to look something like that. So let's see. From negative infinity to negative 1, I am decreasing, which makes sense with my end behavior. And I am concaving up, so I'm going to have kind of that happy face curve. I'm still concaving up all the way to 0. From negative 1 to 1, I am increasing as well. Or I'm decreasing to negative 1, and then I'm increasing from negative 1 to 1, so I'm still concaving up, but now I'm increasing. And then from 0 to infinity, I'm concave down. From negative 1 to 1, I'm still increasing, but I'm concave down, so I'm kind of the curve switches to a frowny face, and then I'm decreasing. So something like that. Okay. So hopefully you have a good variety, some rational ones, some square roots, some polynomials. Hopefully that gives you a good start to that, to the homework. Like I said, I didn't give you a ton on the homework, just because I know they take a while.